waveMesh, a novel method for nonparametric regression modeling. We begin with an introduction to wavelets. Wavelets are basis functions that look like tiny waves. The Haar and Mortlet families are examples of wavelets. Many functions can be expressed as a linear combination of wavelet bases. These basis functions have a number of desirable properties. For instance, they can capture local behavior and offer a sparse basis representation. This sparsity means that many of the coefficients are 0. With the basis expansion for wavelet regression, we minimize the following: a least squares loss term followed by a penalty. W is the basis matrix. The L1 penalty controls smoothness and induces sparsity. We now discuss a limitation of traditional wavelet methods. Traditional wavelet methods require a regularly spaced covariate. Data like this is problematic. A simple solution is to interpolate the raw data to a regular grid. We then work with the transformed data. Specifically, we now minimize the following expression. The matrix R represents the interpolation mapping. This technique is adequate for a single covariate, but a multivariate extension is difficult. Interpolating raw data to a multivariate mesh incurs the curse of dimensionality. Other techniques require estimating the joint density of the covariates, also incurring the curse of dimensionality. Another limitation is the absence of wavelet methods for high-dimensional data. We now discuss our proposal and its extension to additive models. First, recall the original method with interpolation matrix R, which mapped raw data to a regular mesh. Our proposal, called waveMesh, minimizes instead the following expression. The novelty of our method is the interpolation matrix, which maps a function on the regular mesh to a function on the covariate values. The main highlight of waveMesh is that it easily extends to multiple covariates. So far, we have only modeled y as a function of a single covariate. Now, we model multiple covariates via additive functions. This is done by an easy modification of the optimization problem. We can also fit sparse additive models for high-dimensional data by another sparsity penalty. This penalty imposes sparsity in the component functions.